Welcome to the channel. Let's look closely at the two numbers that govern the survival of every distribution utility in the Philippines. The Energy Regulatory Commission benchmarks your cooperative on two specific metrics. SAIDI measures how many hours per year your average customer experiences an outage. SAIFI measures how many times per year that outage happens. If your SAIDI breaches the ERC standard for your utility class, you absorb direct financial penalties. Consistently exceed that limit over time, and you invite an active ERC investigation into your operating franchise. Yet, when we ask operations teams what their current SAIDI and SAIFI numbers are, not the historical figure from last year's annual report, but today's running total, most cannot answer. The data determining your regulatory compliance is being tracked. You need to be tracking it too, day by day. The traditional approach relies on field crews recording outage data on paper forms or calling in oral reports. That data flows to the operations office, gets compiled weekly or monthly, and the final calculation sits waiting for the year-end annual report. By the time you run the math, you are out of time to act. A cooperative finish in March with 6.2 hours of SAID will not realize it is trending past an 8-hour annual target until August, when the accumulated duration has already reached 14 hours. The manual arithmetic is also built on poor inputs. Crews estimate outage start times, durations get rounded off, and affected customer counts are approximated from circuit maps that rarely reflect the actual physical connections. An electric cooperative that assumes its SAID is a safe 7.8 hours, based on paper reports, might discover their actual rate is 11.2 hours when measured strictly against an auditor standard. The calculation methods and benchmark targets we are discussing follow the precise regulatory framework governing utilities here. The ERC's Distribution Services and Open Access Rules, or DSOR, and the Philippine Grid Code. Relying on estimates to measure compliance is a mathematical liability. Surviving an ERC audit requires abandoning manual entry in favor of automated tracking. This diagram shows the formula for SAIDI, the System Average Interruption Duration Index. For every outage, multiply the number of customers who lost power by the duration of that interruption. Then, sum all of those products across all outages in the period. Divide that total sum by your total number of customers served. The resulting unit is your average interruption duration per customer. Consider an EC serving 45,000 customers. In January, they experience 3 events: a transformer failure hitting 380 customers for 4.5 hours, a line fault affecting 2,100 customers for 1.2 hours, and a typhoon that drops 31,000 customers for 8.7 hours. Add those products together, 1,710 plus 2,520 plus 269,700, and divide by the 45,000 customer base. January's SAIDI contribution alone sits at 6.09 hours per customer. Annualize that run rate over 12 months, and you hit 73 hours of SAIDI. The strict ERC benchmark for most Philippine ECs is between 8 to 12 hours annually. Because of that one widespread typhoon event, this cooperative has mathematically breached its annual limit in the first 31 days of the year. This visual shows the safety formula, the System Average Interruption Frequency Index. You sum the total number of customers interrupted across all outages, 380 plus 2,100 plus 31,000, and divide by the 45,000 total customers. For January, the frequency rate is 0.74. Annualized, that projects to 8.9 times per customer per year. The ERC benchmark for most cooperatives is strictly 4 to 6 times. These two metrics diagnose completely different operational failures. A utility with high SAIDI and low safety experiences infrequent outages that stretch for long periods. This exposes poor restoration capability or convoluted fault clearing procedures. Conversely, a utility with low SAIDI and high safety restores power efficiently, but it suffers from distributed, frequent system faults. This points directly to failing equipment quality or inadequate vegetation management along the lines. Both are tracked by the ERC. Addressing one while neglecting the other yields partial credit and ensures continued penalties. Outages fall into 2 primary categories: scheduled and unscheduled. Scheduled outages for maintenance and switching are controllable variables managed by your internal scheduling practices. Unscheduled outages, equipment failures, animal contact, and weather damage feed into your SAIDI and SAIFI calculations as full contributors. They are the objective measure of how reliable your infrastructure actually is. However, the ERC permits exclusions for specific catastrophic events. Severe force majeure incidents like earthquakes and major floods are excluded from regulatory metrics because infrastructure investment cannot reasonably prevent them. For cooperatives in high typhoon zones, this exclusion is vital. A Yolanda-level event will dominate your data, making performance comparison impossible without the regulatory carve-out. Claiming this exclusion requires strict proof. Auditors demand timestamp data showing exactly when the event began, which outages are attributable, and when restoration finished. Manual recording during a disaster does not generate defensible documentation. If your exclusion claim fails an ERC audit due to unverifiable data, you absorb the full SAIDI penalty for the typhoon. Traditional outage detection waits for customer complaints. A circuit fails, staff wait for hotline calls to localize the fault, and they log an approximate start time based on the first recorded complaint. This schematic outlines the TXERA architecture. Current sensors are installed directly on distribution transformers, continuously broadcasting their load status over an MQTT pipeline. When a transformer loses load current, indicating a supply failure, the platform registers the outage instantly. It locks in a GPS-located asset identifier and a millisecond accurate timestamp. The restoration event is captured with the exact same precision. Current returning to the transformer automatically closes the record, providing a flawless duration metric. The affected customer count is dynamically pulled from the customer database, tied directly to that specific transformer, guaranteeing accuracy up to your most recent meter reading cycle. This telemetry calculates your metrics continuously. You can look at your dashboard on June 15th and know exactly where you stand against the annual benchmark, rather than reacting in a panic on December 31st. Accurately collecting SAIDI and SAIFI data is only the prerequisite. Using that data to physically optimize the grid is the objective. This chart shows the first step of the analysis workflow, applying the Pareto principle. You isolate the top contributors, where typically 10 to 20% of outage events drive up to 80% of your total SAIDI. Step 2 categorizes these high-impact events by their root operational causes. Equipment failure, vegetation contact, and weather damage each require distinct, targeted prevention strategies. Step 3 maps those contributions geographically. Heavy concentration on specific feeders or substations reveals systemic infrastructure degradation, rather than isolated random faults. Step 4 calculates the projected mathematical impact of proposed interventions. If you identify the 5 highest failure transformers on a feeder, you can project the exact SAIDI reduction a replacement will yield. Step 5 finalizes the process, building your annual budget strictly around the infrastructure upgrades that offer the highest SAIDI reduction per peso spent. Rigorous data analysis removes the guesswork entirely. It provides a mathematically sound capital investment strategy. An electric cooperative ran this exact analysis and isolated a distinct problem area. They determined that replacing 12 age distribution transformers would have prevented outages contributing 2.3 hours of SAIDI in the prior year. The visual summarizes the financial reality. A 1.8 million peso investment explicitly eliminates 2.3 hours of future SAIDI. Across a base of 45,000 customers, eliminating 2.3 hours of downtime retains over 100 million pesos in service value. Avoiding the regulatory penalties alone completely covered the initial capital expenditure. The Energy Regulatory Commission is measuring your cooperative right now. The financial and reputational consequences are active and continuous. Challenge your operations team to calculate your year-to-date SAIDI and SAIFI today. If you cannot produce that calculation in under 30 minutes because your data is fragmented, you know exactly what your first priority must be. Next week, we examine AI-powered non-technical loss detection, showing how telemetry identifies electricity theft and billing anomalies that manual audits miss entirely. Reliability is measured. Manage what you measure. Subscribe to learn how.